come to the what is the metallic structure, crystal structure. Okay, so this was the unit cell, right? Till now we have discussed the unit cell. Okay, so how they behave and how what kind of the things are there. Okay, now we come to the metallic structures. Okay, so what is the definition? Definition is simple. It describes how metal atoms are arranged in a regular, repeating pattern in a solid state. Metals adopt highly efficient and symmetrical structures to maximize packing density and minimize the energy. Okay, so everything in this world have a tendency to minimize their energy. Okay, this is the universal truth. Okay, so everything in this world exists. They tends to be in a minimum energy. Okay, like the similarly in any kind of a structure, they would try to be in a minimum energy. Okay, so as I have discussed already, what is the crystal structure? Structure means whatever the unit cell that you have, they will repeat themselves in a regular fashion, and what the kind of the fashion, a pattern they have adopted to make the bulk material. So which is known as metallic structure. Okay, crystal structure. Okay, so as we have discussed the unit cell have the three kinds of, which is a simple, then body centered and the face centered. If we talk about the metallic structure, okay, so there are also three kinds. First one is a body centered. Okay, it's it's very similar to that of the unit cell. The the meaning is the atoms are present at the corner of cell or cube, and one atom is present at the center of a cube. Okay, this is the body center. If we talk about the next one is the face center. The face center is similar that to the unit cell, which is the face centered. All atoms are present. I mean, 8 atoms are present at the corner. 8 atom means the fraction of the atoms are present at the corner of the cube, and uh, rest there are the 6 faces at the cube, right? So 8 atoms are present, or you can say the fraction of the 8 atoms are sorry, 6 atoms are present at the edges or at the face of all the cube, right? So as I have already discussed in the previous class, that face centered means the half of the fraction of the metal atoms are present at each faces. Okay, so it means if there are the 6 faces, then means you have the 8 atoms completely present in a face centered cubic cell. Okay, here we are talking about the cubic structures. Okay, and 8 corners contribute only 1 atoms in any kind of the unit cell or the crystal structure, because 1/8 part of the atom is only present at the corner of unit cell, right? Okay, so body centered description is similar. 8 atoms are located at the corners and 1 atom present at the center of the cube, right? If we talk about the packing fraction means the volume occupied by the total number of atoms present in a crystal structures. Okay, so as we know that total number of atoms are present in body center are 2, because 8 corners atoms contribute only 1 atom, right? And 1 atom is present at the center. So how many atoms are present there? Total only 2 atoms, right? So that 2 atoms present will occupy only 68% of your total volume present in a cubic structures. Okay, so what is the coordination number? Coordination number is 8. It means that is the each atom contains 8 neighboring atoms. Coordination number means the atoms which contribute, which connect to the neighbor atoms. So in body centered, you have the 8 coordination number, means the atoms which connect to the near about a neighboring atom, which is 8, and what comes from all of from each corner. Okay, these are the examples, like the iron. Though, okay, if you will heat the iron, okay, if you raise the temperature of the iron, they would not have the same structure. They would not, show the same crystal structure, because as the temperature increases, there, the atoms vibration and atoms movement occurs. Due to that, the configuration and the crystal structures might get changed. Okay, at different temperatures. Okay, so but what the structures that shown by the iron at room temperature is a BCC. Okay, body centered crystal structure. Okay, like the chromium, tungsten, molybdenum. These are the examples of the body-centered crystal structures. Okay, if we talk about the properties, what the kind of the properties that we would have. Okay, if the body-centered structures are there, then this is the high strength. First one is the high strength, but moderate ductility. Ductility is moderate. I mean, ductility I have already discussed yesterday. I mean, this is the how much you can elongate something. Okay, which is known as the uh, uh, ductility and brittle. I mean, before breaking the material, how long you can elongate the materials. That is known as ductility. Opposite to that, this is the brittleness. Brittleness without stretching the things, you can break down directly. Okay, so that is the brittleness. Okay, so it depends. Sometimes it is desirable, and sometimes it's not desirable. It depends on your applications. If your application part has a required, so that I mean, before breaking, you could have the you stretch so that you can replace the material. Okay, where it is feasible, it is desirable. But sometimes you don't want such kind of the things. Okay, so you directly, if it's failed, then it's could break. Then say okay. But most of the time in engineering applications, ductility is desirable because the ductility means before breaking you have the indication. You can see that the material is being failed. Okay, so that you can easily replace the material. Okay, so it's a very kind of the desirable things. Okay. Okay, so now it tend to be the harder and stronger but less ductile. Okay, ductile means already have I told you. Okay, so it has the harder and stronger but less ductility. Okay, if it's a something. I mean, ductility means if ductility is high, then hardness would be less. Okay, just opposite relation, because if something is hard, you cannot stretch them. Okay, so it's just a vice versa kind of. Okay, but here's a moderate ductility, so you could have the moderate hardened as well. Okay, because the common in metals that are stronger and harder. What the kind of, I mean, if we talk about the BCC, then it's very general, very common to be present in a metal. Okay, I mean, if we categorize the material science or material in a broad category, then we have the material in metal and non-metals. So all metals mostly behaves on having a BCC kind of structures. It's not a generalized, but most of the metals exhibit BCC structure. Okay. Now we come to the FCC. FCC means the face-centered cubic cell. Okay, the descriptions are atoms are present at the corners in the center of all the six faces of the cubes. Right. So total number of atoms present is are four. How? The all eight corners will contribute only one atoms. Right. At all the six faces, you have all each faces have one by two part of the each atoms means half. If half atom is present at the one phase and you have a total six phase, then how many atoms are present there? Only six into one by two, which is equal to three. Okay, so three atoms comes from the faces and one atoms comes from all the corners. So that you have all four atoms. Okay, in FCC. That's why you have more packing efficiency, because the if packing efficiency means the amount of the volume occupied by the atom present in a crystal structures. Okay, so if number of atoms are more, it means the packing fraction would be more. Okay, as here you can see, it has a 74%. 74% means you have left 26% only. Okay, 74% volume occupied by the atom present in the structures. Okay, as compared to the previous one, which is the body centered, there are only 68% packing fraction. It means you have the high packing fraction, means you have the higher density. Okay, because the amount of the volume occupied by the atom is more in case of FCC as compared to the BCC. Right, BCC means the body centered cubic and FCC means the face centered cubic, right? If we talk about the coordination number, similar to that of previous, the coordination number means the neighboring atoms. I mean, how many atoms are there? So they contribute the touches to the neighbors. So how many? There are the 12. Each atoms contact with the neighbor atoms. How many? There are the total 12 atoms. So in previous we have 8 atoms. We talk about the coordination numbers. Yeah, coordination numbers are, yeah, 8 atoms, right? So here's the 8 atoms. But in case of the FCC, there are total 12 atoms and 12 coordination numbers. Okay, means the 12 atoms contact with the neighboring 12 atoms. Okay, so examples are aluminium, copper, gold, silver, nickel. These are the examples of FCC. Okay, so aluminium, which is very common, very usable, and very frequently used, you know, material in our daily life. Copper, which is frequently used in electrical equipment. Gold, which is costly. Okay, and most of the person have known that this is a very frequently used, and this is the currency exchange kind of materials. Okay, so every country has their the reserve of the gold, and according to that, they can have their money valuations, right? Silver, you know all very well. Nickel are little bit cheap material. Okay, so they all exhibit the FCC, face-centered cubic cell, cubic structures. Okay, if we talk about the properties, then higher ductility and malleability. Higher ductility means the ductility means the same as you can harm and you can stretch. Malleability means how you can separate, how you can spread the materials. Okay, if you stretch and you can spread the material, that's the malleability. Okay, and if we second one is the more ductile and malleable due to the high coordination number and efficient packing fraction. Why it is being able to show the higher, ductility and malleability, just because of the high coordination number and higher packing efficiency. Okay, packing efficiency means the packing, the amount of volume occupied by the atoms in a structures. Okay, so common metals that are soft and excellent conductors of heat and electricity. The material most of the materials have a tendency to conduct both the heat and electricity. Okay, so common in metals, these are also common in metals, but what kind of the metals? The metal which are soft and excellent conductor of heat and electricity. The conductor, the material who exhibits their conductivity for both heat and electricity, and they are soft. So these are the, under the category of the metals, you have the many kind of you know different subcategories. Okay, so in that subcategories you can have the soft materials, okay, and hard materials. So in soft materials that exhibit mostly the FCC. If we talk about the excellent the conductor, we classify the metals on the basis of the conductivity, and in that conductivity you can get to, categorize what are the materials who conduct the heat and as well as the electricity. So if the material which can conduct both heat and conductivity, they exhibit the FCC. Okay, so this is a common idea. You can have the sense that, what kind of the materials that can show that exhibits the FCC kind of structures. Okay, the third one is the hexagonal close packed. Okay, so description: the atoms forms at the hexagonal lattice with a layers arranged in another A B C sequence. Okay, so hexagonal means you can have like this: one, two, three, four, five, six. Similar to that, you could have like just draw the line here, here. No, it wasn't. Just draw the hexagonal like 1, 2, 3, 4, 5, 6. Okay, if you draw like, yeah. So this is the kind of hexagonal. Six faces are at top, and which is this is the kind of hexagonal, okay, structures. So if we talk about the packing efficiency, it is equal to the, just like the FCC, 24%. Coordination number similar to that of FCC, which is 12. Examples are magnesium, zinc, titaniums. These are the uh, examples of hexagonal HCP. HCP means the hexagonal close packed. Okay. Now, if we talk about the properties, then limited slip systems result in the lower ductility compared to the FCC. So, if we talk about the ductility, it has a lower ductility as compared to the FCC, though they have a similar packing fraction and some similar coordination number, but the regiment is completely different. That's why they have the different ductility as well. Okay, so ductility is lower as compared to the F- FCC. Strong but less ductile due to the limited slip system. The slip system is something which we will define later. Okay, just you have the idea. I mean, what is a slip? Slip means the atom present at the particular place, they just got slip and they try to, I mean, whatever the structure that we are defining, they're not in that position, they have moved somewhere else. Okay, that comes known as a slip. But how they are and how they behave, they will definitely discuss in later on. Okay, so don't worry about that. So slip system is a, in your syllabus we will discuss it in a broad way. Okay, so strong and light weight common in structural application. So why it is used in a structural application? Because it's a tendency of lightweight. Okay, so wherever you are required, no, less weight, you can use these kind of the structures, material basically who exhibit the HCP kind of structures. So strong and light. So it is a very desirable kind of properties because everything in this world we want to have a strong nature. Okay, and lightweight because wherever you want you can easily apply that things. Okay, so lightweight is more desirable in applications. So these are, as you can see, as you can think about that, these materials are more applicable in engineering applications. Okay, so structural, that's why it is used in structural applications. Okay.